Hi everyone, and welcome back to our YouTube channel. In this lecture, I will show you the basic arithmetic operations that we can perform on a given set of matrices. And also, I will point out some important types of matrices that we will be using throughout this lecture series in linear algebra. Alright, having said that, let's first start with the first operation that we can perform on any given set of matrices, which is addition and subtraction. So we can add or subtract two matrices if they satisfy some conditions. So what is this condition? Okay, we can add or subtract two matrices. Actually, I'll first show how we can do that, and then I will define the formal rule that we use while adding two matrices. Okay, the thing is, we can add two matrices of any size, but this size should be equal. So if the size of two given matrices are the same, then we can add or subtract two matrices. What I mean by that, let's give an example first. Let's give a concrete example, and then I will show you the formal rule. So suppose we are given this matrix 2, 3, 4, 5, 1, say 0. Oh well, let's give a name. Suppose we are given a matrix A. Well, actually, how many rows and how many columns do we have? So we have 3 rows and we have 2 columns. So a matrix can be of any size, but the important thing, if you want to add or subtract this matrix to or from another matrix, say let's say this is B, matrix B, then B must be of the same size, because we will add or subtract these two matrices by performing an element-wise addition or subtraction. So we actually add or subtract the corresponding entries in each matrix. So the size of each matrix should agree. So we need to have again a 3 by 2 matrix in order to apply this basic arithmetic operation. So say we have 3, 4, and we have 5, 6, and we have 1, 3. So suppose I want to add these two matrices, then now it is legal. So I can perform an addition on these two matrices. And why is that? That's because they are of the same size. We have a matrix of size 3 by 2, and we have also a matrix of the same size, which has again 3 rows and 2 columns. So when adding these two matrices together, then we have again 3 by 2 matrices, a 3 by 2 matrix. So we just add each component of the matrix with the corresponding entries. For instance, I add 2 to the associated entry. So this is the 1, 1 component, right? So this is the 1, 1 component of A, and this is the 1, 1 component of B. So I just add 2 plus 3. So this is 2 plus 3. And then 3, I add 3 to 4. So I get 3 plus 4. As you notice, this is the 1, 2 component of each matrix, and I continue in the same manner. So I got 4 here and I got 5 here in the corresponding entries. So we have 4 plus 5, and we have 5 here and we have 6 here. So what am I doing is 5 plus 6, and then for the last row I add the elements of the last row to the elements of the last row of the second matrix, which is called B. So 1 plus 1 and 0 plus 3. So what I have here, so applying an element-wise addition, we have 5, we have 7 here, we have 9, 11, 2, and 3. So this is the result. And as you notice, we have a matrix of the same size, which is again a 3 by 2 matrix, right? So this is the rule of addition. And while subtracting one matrix from the other one, we apply the same strategy. Suppose I want to subtract B from A. Okay, let's find the B minus A. And the direction is important, guys, because I am performing a subtraction. So the operation here, the arithmetic operation here is the subtraction. So when I subtract two matrices, when I put one on the left hand side and the other on the right hand side, then this is a matrix. But when I change their locations, if I, for instance, try to compute this matrix, then the values can be different. So just be aware of this situation. Okay, and then having said that, let's find the result. What should I do? I perform an element-wise subtraction. So I subtract each element of B from the element, from the corresponding element in the matrix A. So what I mean by that, so the first element is 3. So we have 3 minus 2, right? And then we have 4 and 3, so we got 4 minus 3 right over here. And I just subtract the corresponding entries. So I just move from one row to the other row. So what I have here, so 5 minus 4, and we have 6 minus 5, and we have 1 minus 1, and we have 3 minus 0. So what we have in the end, so we have a matrix of the same size again, because if you want to add or subtract two matrices, they need to be of the same size. So in other words, the number of rows and the number of columns must be equal for each matrix. So what we have here, this is 1, this is again 1, 1, 1, 0, and 2, and this is the result. And again, we have a matrix of the same size. And if I want to formally define the addition or subtraction of two given matrices, then what can I say about that? Suppose C is the result matrix, andCij's actually represent the entries in this matrix. So what I am doing is, when I am trying to add or subtract these two matrices, for instance, if I am trying to compute A plus minus B, then what I am doing is I just add or subtract the corresponding entries. So it is Aij plus minus Bij, right? So here Aij's are the corresponding entries of matrix A, whereas Bij values are the entries in matrix B. So this is also the formal definition of addition or subtraction for two given matrices. And we can even generalize. We can add or subtract many more matrices, right? We can add 4 matrices as well. This rule works the same. Okay. And another important operation is that multiplying a matrix by a scalar. So multiplying a matrix by a scalar, what I mean by that? So a scalar is just an arbitrary real value. It can take on any real value. So if I want to multiply a matrix by a scalar key, well, k, say, so k is any real number. So k is an element in the real numbers. So this capital R represents real numbers, the set of real numbers, and k is any value in the set. So when I multiply the matrix A by a scalar value or by a real number, then what should I do? So suppose I am trying to compute this say the k is equal to 2, and I want to multiply it by a matrix, say 3, 1, minus 4, 0, minus 1, 2, 3, 0, minus 4. Then what is the result? We can multiply any matrix by a scalar value. That in this case, actually, the size of the matrix is not our concern. What we need to do is we multiply each entry of the matrix by the scalar value. So I just multiply each component of this matrix by the scalar value. So what is the result? So the size of the matrix is unchanged, and multiplying each entry of the matrix by the scalar yields us what? Yields us 2 times 3 is equal to 6, 2 times 1 is 2, 2 times minus 4 is minus 8, 2 times 0 is 0, 2 times minus 1 minus 2, we got 2 times 2 is 4, 2 times 3 is equal to 6, 2 times 0 is equal to 0, and 2 times minus 4 is equal to minus 8. So this is what we obtained in that. Okay. So we can, in other words, as a result, we can multiply a matrix by any scalar value. And what we need to do is just simply multiply this scalar value by each of the entry in the matrix and find the result. And if I want the formula defined, then what it means is, if we have the, if the entries of matrix A are represented by aij's, then this is the result of our multiplication by scalar. So each entry is actually multiplied by the value k. Okay. Unless k is equal to 0, well, we have a matrix, and of course, unless, well, if the result of multiplication is equal to 0 matrix, and a 0 matrix is nothing but a matrix all of whose values are equal to 0, and then if you want to obtain a 0 matrix, then this k should be equal to 0. If we multiply this matrix by 0, then we have a 0 matrix. Or if this is a 0 matrix already, then multiplying by any scalar wouldn't change the result, because multiplying 0 by any real value is again a 0. Alright, and this is the multiplication by a scalar. And let's proceed to another important arithmetic operation, which is multiplication. So multiplication, let's look at the multiplication. Well, first of all, let's give the formal definition. Okay, for the multiplication case. Okay, here's the multiplication. So suppose we have matrix A, and whose entries are represented by aij's, and we also have matrix, say B, who also have entries represented by bij's. And now let's try to find the multiplication of these two matrices. Well, first of all, to multiply two matrices, we need to check out some property. So I will come to that point in a moment. But first of all, let's define this multiplication rule formally. And what we do is just we take the summation over some index k, where this is equal to actually aik times bkj. And I will explain this formal formula, but first of all, let's see a simple example to understand how we can multiply two given matrices. And to multiply any given set of two matrices, what condition should be satisfied? Okay, let's give two matrices. Alright guys, suppose here's the first matrix. 1, 2, 1, 3, 0, 0, 1, minus 1, 2, 1, 0, 0. Suppose we are given a 3 by 4 matrix on the left hand side and we want to multiply it by this matrix. One, 1, 0, 0, 0, 0, 1, minus 1, 1, 2, 1, 1, and 2, 1, 3, 1. So now on the right hand side of this multiplication we have a 4 by 4 matrix. Well, actually the first one on the left hand side represents the matrix A formally, and the matrix on the right hand side of the multiplication represents the matrix B formally with respect to the above formula. Well, because we need to find the result of this multiplication based upon this formula, and how can we do that? What does it mean? So there is something that you should be careful about before multiplying two matrices, is that some property needs to be satisfied before multiplying these two matrices. And this property is, for the first matrix, the number of columns. So here the number of columns of the first matrix, which is A in this case, must be equal to the number of rows of the second matrix, which is B in this case. And as long as this property is satisfied, we can apply this multiplication operation. So again, we have a left hand side matrix and right hand side matrix, and the rule is, well, the rule states this fact: if we want to multiply these two matrices, the number of columns for the matrix A, well, if we generalize it, well, actually A represents the matrix on the left hand side while multiplying, must be equal to the number of rows of B, and B here actually represents the right hand side matrix while multiplying. So this is an important rule. If you want to multiply two matrices, we need to check that this property is satisfied or not. If it is not satisfied, then we can't perform that multiplication. But if it is satisfied, then we can perform the multiplication. That's one thing that we should make sure before proceeding to multiplication. And how we can do that? Let's now get back to that point. Now let's find the result. And actually, we multiply each row by each column. And in the end, what do I have? Let's see. Okay, here's the thing. I take the first row. Suppose this is the first row of the A, and I take the first column of B, and then I multiply the corresponding entries and then sum them up. Okay, what do I mean? Let's first erase and save more space to squeeze the result, and maybe it is better to write it down here. Alright, so here's the thing. So this means 1 times 1, I multiply the corresponding entries. So 1 is here, you see, and 1 is here. So I multiply 1 by 1 plus then the corresponding 2 and 0 plus 2 times 0 and plus 1 times 1 times 1 and plus 3 times 2, so 3 times 2, and this summation is only the first entry of the result. In other words, let's write the newly obtained matrix here, in other words the result of the multiplication, and do the algebraic operations here below. So what is the result here? 1, this is 0, 1 here, 1 here, it's 2, and 6 here, it's 8, right? So this is just the first entry. So I multiply the first row of A with the first column of B in an element-wise multiplication manner, and then sum them up and find the very first entry, so the 1 1 component of the resulted matrix, so which is the result of the multiplication. And I do the same thing for the other rows and columns. So again, I'm in the first row, I take the first row, but this time I take the second column and I apply the same strategy. So this time an element-wise multiplication, 1 times 1 plus 2 times 0 plus 1 times 2 plus 3 times 1. So what do we have here? So 0, 1, 2, 3, and 3 here, and it's 6. So this is the A12 component. And I keep doing this. So this time I multiply the first row with the third column. So I get the 1/3, 1/3 component. And after then I multiply the first row with the fourth column. And I find the other value. So if we quickly do that, 1 times 0, 0, 2 times 1, 2, 1, 3, and 9 here, we got 12 here. So for the last one, we got 0 here, minus 2, plus 1, plus 3, we got 4. We got 4 here. So we are done with the first row. Then what am I going to do? Now, I pass to the second row. This time, I take the second row and I do the same process. So I actually repeat the same process. Again with the first column, second column, third column, and with the last column. And then put the results right here. And for the last row, do the same thing again. I multiply the last row again with the first, second, third, and fourth column, and I put the values right over here. And this is how multiplication works. Alright, so, and one more thing to say about this, then what is the size of the matrix in this manner that we will obtain in the end? So as you notice, the number of rows actually depends on the first matrix, because we take the rows in the first matrix, which is on the left hand side, and whatever the number of rows of the left hand side matrix is, then our result will have the same number of rows. In this case we have 3 rows because matrix A has 3 rows. And what is the number of columns? Well, and the number of columns depends on the number of columns in matrix B, because we multiply each row by each column included in B. Since we have 4 columns in B, then we have 4 columns. So in the end we should have a 3 by 4 matrix. If we generalize this idea, so what can we say? Suppose we have an m by n matrix on the left hand side, okay, m by n matrix, and we want to multiply it by an m by p matrix where m, n, and p are positive integers. Okay, well, since this is to represent the matrix A and this is to represent the matrix B, and we'll look at the number of rows in A, which is m, and number of columns in B, which is p. So in the end we have a matrix of size m by p. So the obtained matrix, which is the result of multiplication, should have m rows and p columns. And of course, before multiplying, if you notice that the number of columns in A is equal to the number of rows in B, otherwise we will not be able to perform this multiplication. And one more thing, okay, let's get back to the formal definition. And this is actually how we multiply to matrix. And if you notice the formal definition, actually we take the summation over some index k. And in this case, if you look at the formula here, it may seem to be as if we had three unknown variables like I, j, k. But don't forget one thing, actually we know what is I and what is j, right? Because if you want to find the C11, which is the actually the component that is lied at the intersection of the first row and the first column, then we know what the value of I and j is, and I is equal to 1 and j is equal to 1, and the only thing we don't know is the k, right? So, and k here is actually you know, depends on the number of rows or depends on the number of columns. And the number of columns here is actually the number of columns of A should be equal to the number of rows of B. That's the way we perform our multiplication, right? So K just represents that number. In other words, when we run this formula, say 1, 1, we actually try to find this A1K times BK1 over K. And if we take K is equal to 1, then what we have? Let's give some values to K to see how this formula really works. So if we take the value 1 for K, then we have 1, 1 times 1, 1. Plus, if we assume that K is equal to 2, then what we have? Then we have 1, 2, A1, 2 times B2, 1. And it keeps going this way, right? If we have 3, then that means we have A1 3 times B3 1. And what does it mean? So if you notice, the entries of the matrix A are represented by Aij, so A1 1, A1 2, and A1 3 are just the entries of the first row. So, and the Bij values, if you notice that B1 1, B2 1, and B3 1 are the entries of the first column of the matrix B. So we actually multiply the first row of A with the corresponding first column of B in an element-wise multiplication manner. So, and where it will end up? Well, this formula will end up, it depends on what the number of K is. So, which value we choose for the K, right? So the number of actually, you see, here, if K is 10, and that means we have 10 columns, right? If we take K is equal to 10, then this will go to what? This will go to until we have A1, well, say K is equal to 9 for the sake of simplicity. So that means we have A19 times B91. What this means? So that means actually, since the Aij values are the entries in the first row of A and it ends up at the nth position, we have 9 columns in matrix A. And Bij values are the first column elements. So if ends at nth component, that means the matrix B has 9 rows as desired, because the number of columns in A must be equal to the number of rows in B. This is how we actually form our formula to multiply two given matrices. And as you see, this works perfectly. So everything is accurate here. All right. And another important operation that we can perform on a matrix is that finding the transpose of a matrix, and taking the transpose is nothing but swapping the rows with the columns. So we show the transpose by this T symbol, capital T symbol above a matrix. So A to the power of capital T, actually this T represents taking the transpose of this matrix, where of course A is a matrix. So, and this means that we swap the rows with the columns. Okay, what does it mean? Suppose we have a matrix 2, 3, and 4, 5. Then taking the transpose means, all right, so we have 2 rows, right? Here the first row and here the second row. And if we take the transpose, then rows become the new columns, while columns become the new rows. So if we have a square matrix, the size of the matrix wouldn't change. So the first row becomes the first column. It becomes 2, 3, and the second row becomes the second column, or vice versa. Now actually first column becomes the first row, and second column becomes the second row. They just exchange their rows, right? Rows become the columns and columns become the rows. So if I want to formally define, if a matrix A is represented by Aij values, then its transpose can be represented by what? So we just switch the rows of columns and rows and it becomes Aj, right? So we just switch the positions of I and j. Here it was Ij and now Ji, right? Because we changed the rows and columns. Okay, we exchange them. Alright, these are the very important operations that we can perform on a matrix or on a given set of matrices. And I also want to point out some important types of matrices, okay, that we may come across in this lecture series or in any problem related to linear algebra. And the first type is, it is better if we know that we have the expression, we have the terminology here, we have some terminology. For instance, if we hear the name row matrix, so this is a type of matrix, and as the name suggests, it has only one row, and that means we have one row and as many columns as possible. So this is actually an example of a row matrix. So we have only one row, as you see, but we have 4 columns. So this is possible. So this is a 1 by 4 matrix, which is called a row matrix. And we can also have a column matrix. And this time again, as the name suggests, then our matrix is represented in the column form. Now we have one column. So say these are the values, and now what we have, as you notice, we have many rows. In this case we have 4 rows, but we have one column. But it is possible to represent a matrix in this column form, and this is called a column matrix, where we only have one column but arbitrary number of rows. Okay, let's define another type. And we already know actually, but let me again remind you that if we have a matrix where the number of rows equal to the number of columns, then it is called a square matrix, right? So n by n matrix is a square matrix, and which is important for us when computing determinant or finding the inverse of a matrix. That would be extremely useful for us. This is called a square matrix. But if the number of rows and columns are different, then it is not a square matrix. It is just a rectangular form of a matrix, right? It's a rectangular array actually. Alright, let's keep going. And another type is the zero matrix. And what is a zero matrix? And a zero matrix could be of any size. It can be a square matrix or not. But the important thing is, as the name suggests, you can clearly take a guess, all the entries should be equal to 0. So whatever entry included in this matrix must be equal to 0. Then it's called a zero matrix. So the size doesn't important here. So it can be an n by n, or it can be an n by n matrix as well. The important thing is that to be a zero matrix, all the entries must be equal to 0. And another type of matrix, well, these types of matrix are extremely important, that we should be really familiar with these definitions. A diagonal matrix, another important type. We will use, well, actually we will take the advantage of this type of matrices later on in this lecture series, but for the time being, just try to understand what the definition says and what is a diagonal matrix, because I will be using this terminology from now on. And the diagonal, well, we know we have the principal diagonal or the main diagonal. And what was that? Let me give you an example, okay, to clearly state what this means. So say 2, 4, minus 6, 0, 0, 0. Well, this doesn't look like 0. Let's make it, let's raise it and make it look like a real 0 here. Okay. Alright. Now, and fill the rest of the matrix with 0 values. And here comes the diagonal matrix. And then, so what could be the definition? Alright. When I draw this line, guys, you know, starting from the upper left corner of the matrix, making our way all the way down to the bottom right corner, if you look at the entries on this line, they are called the principal diagonal or main diagonal entries. And diagonal matrix, the definition of diagonal matrix states that if a matrix is a diagonal matrix, in other words, then all the entries besides the diagonal entries must be equal to 0. So in other words, all non-diagonal entries must be equal to 0, as you see here. So all the non-diagonal entries, in other words, the entries below the diagonal or above the diagonal, are all equal to 0. Then this type of matrix is called a diagonal matrix. And you will see later in this lecture series that it is really convenient and very advantageous to have a diagonal matrix, especially while computing the determinant or finding the adjoint matrix or doing some other algebraic operations, performing some algebraic operations on a diagonal matrix would be easier. I am not shown you how to compute a determinant or how to find the adjoint of a matrix yet, but I will be doing so later in this lecture series. And when I am doing so, actually having a diagonal matrix would be an advantage, a real advantage. Also, in the advanced lectures, when we come to that point, I will show you how to diagonalize a matrix. So diagonalization is also an important point in linear algebra. Alright, this is another important type. And one more definition, actually there are some others, but another important one is a scalar matrix. Well, what is a scalar matrix? So we may want to take a guess depending on its name. Scalar matrix is actually, it is a matrix, it's a diagonal matrix first of all, but with equal diagonal elements. So what do I mean? So since it is a diagonal matrix, then all the entries besides the diagonal ones must be equal to 0, and the diagonal elements, so principal diagonal elements, must be equal. So this is something like this, right? So I just make up some values for you. So, well, is it a diagonal matrix? Yes, it is, because when I look at the principal diagonal, and if you examine the values below the diagonal and above the diagonal, they are all equal to 0. That means this is a diagonal matrix, and all the diagonal entries are equal to each other, so they are all 7, right? So this is called a scalar matrix. And do you wonder why it's called a scalar matrix? It is simple, because since they have a common term 7, I can take out this value 7, right? So I can write this 7 times, then what? 1 0 0 0 1 0 and 0 0 1. This means, well, actually now I have another important type of matrix here. I will come to that point soon. But as you notice, I turned my matrix into something like, say this is a matrix A, then this is the scalar value k, right? Any arbitrary value k. So now we have a k times I matrix. So that's why it's called a scalar matrix, right? We take out the scalar that is common in all main diagonal entries and write this matrix in this form. So it is possible. Another important type of matrix, well, which is really important, especially when we compute the inverse of a matrix, identity matrix. And what is an identity matrix? Well, actually, this matrix is an identity matrix of size 3 by 3. An identity matrix is this, guys. So on the main diagonal, I only have ones. All the values on the main diagonal are equal to 1, and the rest of the values are equal to zeros. So below and above the main diagonal, we have all the entries that are equal to 0, and on the principal diagonal we have only ones but nothing. So this is called an identity matrix. And if we have an n by n matrix, so if the size is n by n in short, then this identity matrix is represented by I n by n. So this value represents the dimensions of this matrix. So we have n rows and n columns, and n is an arbitrary positive integer, and this is called the identity matrix. Okay, let's continue. Another important one is a symmetric matrix. Symmetric matrix. Symmetric. This is also very useful. We will make use of this matrix as well. The reason why I actually define and show you these types of special matrices is because I'll be using all of this from now on. In the following lecture series, I will make use all of this matrix types. So you should be familiar with all of this. And symmetric matrix, the definition is simple. We take the transpose of the matrix, and if the transpose of the matrix is equal to itself, so if A transpose equal to A, then we call that matrix as symmetric. And right, so let's give an example. For instance, if we have a matrix like 3, 5, say 3, 5, and 5, 6, right? What does it mean for us to take the transpose? Well, we swap the rows with the columns. So it is just a role exchange between rows and columns. Taking transpose means this. So if this is the matrix A, right? Say this is the matrix A, then if you take the transpose, first row becomes the first column. Okay, let's write it. Now first row becomes the first column, and second row becomes the second column. So what we get here? If you notice that this is the transpose of A, right? And this is the A itself, and they're equal. And this matrix is called symmetric. That's the definition of a symmetric matrix. Another important one is a, well, let me mention about this one as well. It's called a skew symmetric. Okay, a skew symmetric. It is a little difference compared with the symmetric one, the skew symmetric. And why? Well, a little change on the definition. This time we again take the transpose of matrix A, but we don't check to see whether or not it is equal to itself, but this time we check if it is equal to minus A. So there is the sign here, so we just check it. If A transpose equal to minus A, then it's called a skew symmetric matrix. Alright, then let's give an example to this one as well. Say we have a matrix like, alright, 0, minus 3, and 3, 0. So then, suppose this is the matrix A. And how about the transpose? Okay, let's take the transpose. If we take the transpose of this matrix, okay, we exchange rows with columns, then what we got? So the first row becomes the first column, right? So 0, minus 3. And the second row becomes the second column. This becomes, that's excellent. Now let's look at this matrix closer. Let's take a look at that closer. So if you notice that actually, well, this is somehow seem to be as if it is closer to matrix A, but there is only a difference between the sign of this matrix and the original matrix A, right? If you notice that if I multiply minus 1 and write this matrix like this, then what we get? So actually, right, you see, multiplying by 0 doesn't change the result, but you see, multiplying by a scalar, we multiply each entry in the matrix by that scalar. And if you notice, if I multiply this minus 3 by minus 1, then we have 3, so the transpose value. And if I multiply 3 by minus 1, we have minus 3, so the transpose value. But what is this? This is minus A, right? So the transpose of this matrix is equal to minus A, which means that this matrix is skew symmetric. Right. And two more important definition. Actually, you're familiar with one of this, which is called upper triangular. And I can see that you all smile when you hear this name, upper triangular, because we pretty much are familiar with this one, right? And from where? because while applying Gaussian elimination or Gauss-Jordan method, actually, if we have a square system, right, when the number of actually the size of our augmented matrix, well, let me put it that way, if the size of our, if you take into account the size of our augmented matrix, and if we have equal number of rows and columns, then we have a square matrix. And if we have a square matrix, and then when we reduce it to the row echelon or reduced row echelon form, actually in the end we have an upper triangular matrix. And upper triangular matrix means what? This means that we look at the values below the main diagonal, and they all must be equal to 0. And to have an upper triangular matrix, we need to have an n by n matrix. So suppose we have a 3 by 3 matrix for a simple case, then let me give you some values here. So 0, 0, and 4, 1, and 2. So we just check to see whether or not we have all zeros below the principal diagonal. Okay, if they're all equal to 0, well, as you notice, this is actually row echelon form, right? We have the strictly increasing number of zeros. So if we have a square matrix, which is an upper triangular one, actually we have a row echelon form. This is what we want to find in the end of the Gaussian elimination, right? So how about the reverse angle? In other words, what happens if we have all the, all the values above the principal diagonals equal to 0? Then this time it's called a lower triangular. Lower triangular. And what do I mean by that? Okay, I'll show you in a second. So actually lower triangular is the reverse way to look at the triangular form. So again, I have the main diagonal entries. Let the size again be 3 by 3, but it does not need to be, right? We can generalize it. We can make it n by n. All you need to do is just look at the values below or above the main diagonal. If below the main diagonal we only have zeros, then it's called an upper triangular one. But if above the main diagonal we have all zeros, then it is called a lower triangular. So in this case, in this example, we have a lower triangular one. Why? Because all the components of this matrix that are above the principal diagonal are equal to 0. And the term upper or triangular, upper or lower, you may get confused a little, because when we say upper triangular, actually we look at the values below the main diagonal, but the definition, the technical definition is saying, well, if I is strictly greater than j and all the aij values are equal to 0, then we have an upper triangular. So if you notice, where I is strictly greater than j, and if this condition is satisfied, then we have an upper triangular matrix. Well, technically we can define an upper triangular matrix in this way. For all this universal sign, you see, for all, that means for all, universal inclusion. So for all I is strictly greater than j, if aij's are equal to 0, then this is called an upper triangular. So the upper comes from here, you see, I is greater than j, right? So we have, you look at the components, this component is 2, 1, right? I is greater than j, and this is 3, 1, right? 3, 1 component, and this is 3, 2, and upper comes from that fact. And how about the lower? Well, in the lower one, the definition works in the reverse way. So this time, where I is less than j, we check to see whether or not all the values, all the aij values are equal to 0. So for all I is strictly less than j, we check to see if these values are equal to 0. And in this case, you see, for instance, 1, 2. This is the 1, 2 component, right? This one. And this is the 1, 3 component. And I is less than j. And this is actually 2, 3. And we exclude equality sign in each of these formulas, right? Because equality means the principal diagonal entries. So we exclude those values. Alright guys, I hope that you enjoyed this video as well. Well, in this video, let's recap. We learned all the arithmetic operations that we can perform on a matrix or on a given set of matrices, like addition, subtraction, multiplying by a scalar, multiplication, taking the transpose. And also we learned many important types of matrices that we will come across during any linear algebra course, like row matrix, column matrix, square matrix, row matrix, diagonal, scalar, identity matrix, symmetric and skew symmetric matrix, and upper and lower triangular matrix in that. And of course, there will be always more of these matrices. There will be other types of matrices, but this is enough for this lecture. And hope you enjoyed it, and see you in the next lecture, guys. And until then, have fun.